Hello world! Thanks to all of you, the channel has reached the milestone of 1000 views. Yay! So on the last video we were talking about regular numbers, and I'll leave the link in the description, and we came up with a solution to the problem which was in O n log n, but there was an assumption I made. Let's see.
I guess the naive way is just to go through each one and check if they're regular.
And the problem is that going through each number is always going to put an n on our big O, right? So what if instead of going through each number, we could just generate the numbers? So let's start small again and start thinking about the powers of 2. Can we generate the powers of 2 without going through each number? Yeah, we can start with 1 and then just multiply by 2 and multiply by 2 and keep multiplying until we go over our target number, right? And that's easy, and we can easily do this with a for loop, but when we add 3 and 5 it's going to be confusing, so I'm coming from the future and telling you we're starting with recursion. By the way, this is assuming, of course, that from in our function is a regular number. And what's the time complexity for this? Well, we're generating them one by one, and how many of them are there? So from 1 to n, we're looking at the powers of 2, so that's about the log of n base 2. But the base doesn't really matter here since we just multiply by a constant, so we can say just it's O log n. So we're taking O log n to come up with these numbers. So what happens when we throw now the prime 3 into the mix? So now we have to keep increasing the exponent of 2, which is what we're doing here, but we also have to take care of the exponent of 3. So we can imagine this as a two-dimensional grid where on one axis we have the exponent of 2 and on the other axis we have the exponent of 3, and we just want to walk on all these squares as long as we don't go over n. And I guess the easiest way is just to walk from left to right, so we're increasing the power of 2, but then when we get over n, then we reset the power of 2 but increase the power of 3. So it's similar to counting numbers. When we get to 9, we reset the digit to 0 and the next digit increases. So that's what we're going to do. Seems reasonable. Let's see. Just so our code doesn't get too messy, I will create a struct to hold the exponent. And if I do it like this, it's fine, but I keep having to recalculate the value of the number every time, so I will add a field to also remember the value, since the value can be calculated from the exponent and vice versa. This will just get dangerous, because if I construct it somehow the wrong way, everything will fail. Let's refactor the code to use this new struct. And right now you must be thinking, well, I can fix this code, I can make it better. And then my refactoring sense is also tingling, but let's focus on the problem here, and we need to add the exponent for 3, we're not increasing it. So let's see. When we get over the target, instead of just standing, we now increase the exponent of 3. But what's the value now? So I reset the exponent for 2 and I increase for 3. So I think we also have to remember the power of 3 that we're working with, but that's going to make things too confusing for me. So I'll just, when I reset a power, I will just calculate everything again. So the value now we'll need a power function for that. So I'll just write my own here, no big deal. We could use a library for that, but whatever. I know, this sucks. Yeah, if you put in a negative number, it will blow up, whatever. Let's keep going. And now if I provide the value to my struct, it won't need to calculate it, but if I leave it blank, it will just calculate it for me. So that I think is a reasonable solution. Okay, we have our solution here, all regular numbers up to 100, and then we get some weird stuff there. Yeah, because I forgot the stopping condition, right? When we go over all the exponents of 2, when we go over the target, we increase 3, and then we just keep increasing 2, but there will be a time where we cannot increase 2, but we also cannot increase 3. So this will happen when I'm on this column right here. That means the exponent for 2 is 0, and I'm also over n. So let's put it here. Oh, somehow it worked. Okay. And you might say this is out of order because it's 1, 2, 4, then you get 3 later, 6, 12, then you get 9. It's out of order. Yeah, I wouldn't say it's out of order. I would say it's just in a different order, right? So we're looking at the order of the powers of 2, of the exponents. So we're looking first at the exponent of 2, then the exponent of 3. We're not looking at the order of the numbers, the usual order, which is 1, 2, 3, 4, 5. But it's not out of order, it's just in a different order. So you have to be open-minded. But can you change this code? So you generate the numbers, not look at each one. You generate the numbers, but it's also in the usual order. I'll let you think about that because I couldn't. So anyway, there we have it, the solution with 2 and 3. How do we big O this? The time complexity for this is a bit weirder, right? But the easiest explanation I can come up with is if you look at each line, if you look at the first line, we already know this is log n, right? Forget about the base, it's log n. And if you look at the first column, it's also log n. This one is base 3, the other one is base 2, but we don't care about the base, so it's log n and log n. And this is a little, like a triangle there. So it's a triangle with log n. This will be log n squared, log squared of n, but over 2, but doesn't matter. So yeah, log squared of n. This is a rare big O, right? We don't usually see log squared of n. But we're still missing 5, yeah. So we have 2 and 3, we're still missing 5. But 5 is fairly easy to add right now. We just do the same thing we did to add 3, but with 5. Okay. Yeah, looks correct to me. We have the powers of 2, then we have a column with the powers of 3. And then we're now walking in 3 dimensions, right? So we did the triangle there, and then we go to, we go on the 5 dimension, the dimension of the exponents for 5, and then we have a smaller triangle there. So looks cool, makes sense. And this is, of course, you have log n here, and log n here. It's all log cubed of n, so it's an even rarer complexity. Last thing, it was fairly easy to add 5, right? Maybe we want to add 7, even though the definition of a regular number is 2, 3, and 5. Who cares about that? We can do sort of regular like, where we also include 7. Why stop there? We could include also 11, 13. What if we make a variadic template where the user provides a list of different primes? This will be on the user. We won't check that. So they provide a list of different primes with at least one prime, and we generate the regular like numbers up to n. So that's a challenge, and this will be in O log k of n if we keep doing this, where k is the number of primes the user has chosen. So I'll do this just to prove that I can, but it's going to be like a quick and dirty, shitty code. Let's see. Well, after 3,000 hours of trying to get this to work, this was the best I could come up with. I think it's fairly cool. So we're calling here regular numbers, even though it's not regular, it's something else, up to 100. And then this calls regular numbers with this argument, regular like 2, 3, 5, 7, 11. And this regular like is a struct where we have an array with the exponents, and we have the value, which is calculated by this member function. And then we have also a member function to calculate the next regular like number. So yeah, try it yourself. See if you can come up with a better solution. And if you can, comment here saying my solution is better. Yeah, last thing I forgot. We should compare our solutions, right? We had the first solution in the short video, which is O n log n, and we have our solution, which is log³ of n. So of course, in the long run, when we have a big n, the log³ is better, right? Obviously, but what about smaller n? Since we're just using ints, n is always going to be fairly small. Maybe the other one is quicker. Let's run both and compare the times. Yeah, so I just copy and pasted the two solutions. I didn't include the template one since we would have a bunch of name clashes there, but the template one should be pretty much the same as the second one. So let's compare it. Let's see the results. So the first one takes, it's in nanoseconds, so 3 million nanoseconds, so 3,000 microseconds, 3 milliseconds. And the other one doesn't even get to, it's just 2 microseconds. Okay, so what if we put a smaller number? Yeah, pretty much the same. What if it's a pretty big number? Yeah, it's still much faster. So there you go. So there you go. This time Big O didn't lie to us. Okay, see you next time. Bye, world.